In the previous lesson, we took a look and experimented with implementing combinatorial logic in a CPLD. But in this lesson, we're going to take a look at the other type of logic used in CPLDs and FPGAs called procedural logic. Procedural logic uses input signals like a clock or reset to drive state changes in outputs, similar to the clock in this shift register that we designed in the Introduction to Digital Electronics course. Let's look at a quick example of procedural logic in VHDL code. This example will output the clock input divided by 2. Here we have the basic entity, reset and clock as inputs and an output. We use a signal called CLK div to connect our procedural logic to the output. Procedural logic in VHDL is done in a process. Here we have a process statement named divide by 2. A process should include what is called a sensitivity list. If a signal listed here changes its state from 0 to 1 or 1 to 0, then the process will run. So we list the reset and clock input signals here. Inside of the process, we first check to see if reset has been activated, and if it has not, then we check for a rising edge transition on the clock changing from logic 0 to logic 1. If the reset equals 1 statement is true, meaning that reset is a logic 1, then the CLK div should be set to a logic 0. However, if reset is 0, and if the clock just transitioned from 0 to 1, then CLK div should be set to the opposite of its current value, from 0 to 1 or from 1 to 0. Since clock div is updated only on the rising edge of the clock input signal, the output from clock div will be half the frequency of the clock input, creating a divide by 2 effect like you see in this timing diagram. In the Introduction to Digital Electronics course, we were introduced to delay flip-flops or D flip-flops for short. For this lesson's experiment, let's build a custom D flip-flop in a CPLD. In addition to the typical clock, data, and output Q pins, let's add a reset input and a clock divide by 2 output. So first, we'll need to make the Quartus 2 project. We'll use the new project wizard. I'll save the project in the FPGA/Lesson 5 folder on my desktop, and the project name will be Lesson 5. We'll be using the EPM 3032 ATC44-10 CPLD device, so choose that one. Then click Next and finish off the project creation. Now, with the project created, go to File, New, and add a VHDL file to the project. And let's start coding. First, we'll need the IEEE library and standard logic libraries. The port description is pretty simple. Reset as an input, clock as an input, data input will be called button 0, the clock divider will be called LED 0, and the D flip-flop output will be LED 1, and then we end the entity Lesson 5. The architecture will be named RTL, and we will use 2 signals in this architecture, one for the divider called blink, and data for the D flip-flop output. Now we'll start building our D flip-flop using a procedural logic process called data register 0, with reset, clock, and button 0 in the sensitivity list. Remember, if any of those input signals changes, this process will execute. So now we can begin the process description. If reset is 1, then data and blink should both output logic 0. Otherwise, or else if, the clock is a rising edge, then data should output whatever button 0 input is, and blink should output the opposite of its current value. Then we end the if statement with an end if, and we end the process statement with an end process. Lastly, we assign the signals blink and data to the respective LED 0 and LED 1 output signals, and end the architecture RTL. Now save the VHDL file as lesson5.vhd and compile the design. As you can see, the compile didn't go through because I made a boneheaded mistake. LED 0 and LED 1 should be described as outputs in the entity port, not input. So I'll fix that mistake, save, and recompile the design. This time, things go smoothly, and the compile finishes. So now let's look at the pin planner. In the entity port, we commented which input and output pins should connect where on the CPLD. So let's input them here since the fitter chose all the wrong pins. Then we once again recompile the design, and when it finishes, we go back to the pin planner, and this time the pins connect to the port inputs and outputs correctly. From here, we'll move over to build the hardware schematic. The schematic for this project starts out with our power regulator, which uses a 9-volt battery input to an LM317 with two resistors that set its output to plus 3.3 volts. Two 10 microfarad bypass capacitors make sure the circuit has enough current to operate. We'll also add a resistor and LED from power to ground to notify that power is good. The CPLD connections are 3.3 volt to all of the VCC pins and ground to all of the GND pins. Then a resistor and LED connect from pin 21 to ground, along with another resistor and LED connecting from pin 22 to ground. We also have a push button that connects from pin 23 to power with a 10 kilo ohm pull-down resistor on the pin 23 side. Lastly, we'll use a 10 kilo ohm resistor to pull down pin 44, the reset pin. This means we'll never need to reset the device. Next we have our clock generation circuit. This consists of an ICM 7555 timer. V+ and reset pins of this device connect to plus 3.3 volt power, and GND connects to our circuit ground. Then pin 3 connects to the CPLD global clock pin at pin 37. To set the timer module output frequency to around 10 Hz, we use two 10 kilo ohm resistors and a 10 microfarad capacitor, which connects to pin 6 and 7 of the timer module. And that completes the hardware circuit. Now let's get building. Here are all the parts we'll be using in this experiment. The larger parts are a jumper wire kit, components kit, and a breadboard. The smaller parts from the components kit are a CPLD breakout board, LM317 voltage regulator, three 10 microfarad capacitors, three 470 ohm resistors, a 240 ohm resistor, a 390 ohm resistor, four 10 kilo ohm resistors, three red LEDs, an ICM 7555 timer module, a push button, and a 9-volt battery connector. Now we'll build up the circuit part by part in a slow time lapse so that you can build the circuit with us. Feel free to pause or replay this portion of the video as needed. And with the hardware built on our breadboard, let's power it up, connect the JTAG cable to the breakout board, and connect the JTAG cable to your computer. Now finally, after all that work, open up the Lesson 5 project on your computer and program the CPLD. Here you can see LED 0 is blinking on and off, and it's about half the frequency of the clock input, or about 5 Hz. And if we press the push button whenever the clock rising edge occurs, LED 1 turns on. Since our clock input is fairly slow, it is actually possible to press the input button faster than the clock, so that no output shows. We've seen this effect before in the Introduction to Digital Electronics course, and an easy way to make this go away is simply to speed up the clock. In this lesson, we explored the procedural logic power of CPLD and FPGA to take an element like a D flip-flop, which behaves in a procedural and sequential manner, and customized it for our own specific needs into a logic element with a clock divider inside of it. This ability to use a clock signal combined with customizable procedural logic is one of the things that makes CPLDs and FPGAs so powerful, allowing them to output specifically timed signals, for example, video signals to an LCD. In the next few lessons, we'll explore this power to keep track of timing in further detail.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
Now that we've been introduced to procedural and combinatorial logic, it's time to see how we can keep track of timing by designing a binary timer.